Hello everyone. So I was watching the previous video, the binary search tree part 1, and I noticed that it's kind of like a fixed on a one particular slide, unfortunately. So I'm just gonna explain to you that that was the chapter 25, and I talked about especially at the end of the example at the end, I talked about this two binary search tree that we have and explain which one is. Both of them are binary trees, but the first one is a binary search tree because of the the fact that the properties of the binary search tree is maintained, and the second one is not. And so it's kind of the examples kind of left out from the video. And also I explained this vocabulary or terms. What is the root? What is a left child? What is a right child? What is a leaf? Length, sibling, depth, level. So unfortunately it doesn't show any of these slides on the video. So as you're watching the video, I would suggest you open the chapters, and watch this 5, 6 slide of basically the entire video is talking about these 5, 6 is the first few slides of the chapter 25. We talked about tree first, and then we talk about binary tree, and then we'll talk about binary search tree specifically and its properties. So as you remember, there are two main properties we need to maintain in order to consider a tree a binary search tree, and that's first one is being the no having no duplication, and then second one is, and which is the most important one, is for any node inside the tree we want to make sure the values on the left side of nodes are smaller or less than the values of the node itself, and the value of the right side of the node are greater. So every time we're adding, removing, or even trying to just traversing the binary search tree, we want to make sure that we're maintaining these two properties. Otherwise, then the tree is no longer is going to be the binary search tree. So we also explained the binary search tree representation of it as kind of look like a link of some nodes that we call the nodes, the tree nodes. The tree nodes are going to hold the, as you can also see on the slides, they can hold the elements that we're trying to value, that we're trying to store. And then also, since each node is going to have children's, a maximum number of children, since we're dealing with a binary tree, is 2. So you either have a left child or right child or none of those, or basically both of them, right? So the maximum number of children you can have is 2. And so it's similar to the linked list structure. Each node is going to reference to its both of their children. One is considered the left one. Again, that's just the representation of it, and the other is the right one. So we're going to implement that as well together, and so of course you can imagine we're going to finish it this week, and next week you're going to have it as an in-class assignment for submitting, or offline assignment, submitting it in the e-learning. So the nodes, as you know, like in same thing in linked list, the nodes are just going to hold the elements and who is going to be the next child. If it's root, for sure we know that then that somebody has to point to it, right? So at least otherwise we're going to lose it, right, in the memory. So it's kind of like a head of your linked list. It's also similar concepts. Root is the head of your binary search tree. So if you lose the head node, then you're completely going to lose entire binary search tree structure, because in the memory, because as you can see, each node is only going to know who's are their next, right, their children. They don't really know who are their parents. So because of that, we need to have another structure, another class to be the owner of these nodes and maintaining this entire link of these 3 nodes for us. So we call that one the binary search tree class itself, right? So we need 2 class, one the binary search tree class, and the other is going to be the 3 node class. The methods that we're going to implement, pretty much the implementations are available on the slides too, so we're just going to redo them, and you see that these are all generic types. All right, so there we have the E, and we already talked about generic. Here is a search method. So it's the search method is going to be the simplest one, and we also want to talk a little bit about the efficiency of binary search tree. And it's obvious inside the search, right? So when you are having a binary search tree, and as you are implementing your binary search tree, if you really try to maintain it in a way that all, every children on the left are going to be less than all the children on the right, and from the node, and all the other children from the right is going to be less than the root. So that way, when you're searching, you don't have to search an entire tree. You either go to the left or to the right. So basically, you're only going to go through one single path from the root to that particular node that you're searching for. So it depends how lucky you are. Is the node that you're searching for is somewhere in like level 2, 3, so it's going to be immediately like order of 1, and you're gonna hit that. Or if the height of your tree, and we talk about the definition of the height. If the height of the tree is like 10, 20, or n, so then sorry, not the height of the tree, but the number of the element in the tree is n, and so the height of the tree can potentially go to really long, right? So but you don't really need to do n single comparison to find the element. You either go to the left or right, so you're only going to go to the height of the tree, and only one branch, really, like just one branch, and we are going to find. So we're going to see some examples, but this is the code for it, right? So if I'm looking for the element, in this binary search tree, I have to start from root, because again, it's only only reference, only head that I have to this element, to this root, to this binary search tree. So we're going to start from the root. If the root is null, I'm not going to even continue. I know I have nothing to search for. So I'm definitely, that means this key element that I'm searching for, it is not even inside this binary search tree. But if we do have the root, then we're going to have this while set root. Like very similar to what we had in the linked list. But the linked list, when we have the while, we just keep going to next, next, next. Here, we had to decide. So we need to do some comparison. We either have to go to the left, or we have to go to the right. And basically, the left and right are next, but we have 2 different next, right? So one is in the left side and one in the right side of our node. So starting from the root, so current is going to be our root, and so of course if it's null, we're going to stop and we're going to send false. It means it's not there. But if not, then we're going to start going and checking the elements. So the elements is going to be, if the element is less than the current element or the root, then definitely we will have to look into it inside the left side of the tree. We don't have to go to the right. All right, because it's a binary search tree. So for every single node that we have, the value in the left side should be less than the value of that node particularly. So the current element, if it's bigger than the new element, the element that you're searching for, then definitely you have to go to the left of it to find it. So we're going to the current left. So then the new current has become the current left. Otherwise, if the element is bigger than the current element, that means we have to look for it in the right side, and it's not going to be in the left side, right? So based on the property of binary search trees, so we're going to the right. So we're going to change the value of the current. And otherwise, that means if it's not any of those, or it's not bigger or smaller, that means it's a match, right? So if it's a match, then that means we'll find it. And so since we don't have duplications, we know that's only one, so we're gonna just return true. Since we're only gonna go over one branch, it's not going to take us order of n. So we're not going to do n comparison. We're only going to go through one height of this tree, and that's going to be order of log n. We already know that, right? So we already talked about the binary search, and how the binary search works. Now the binary search tree also going to have same performance as well. This is also the same concept for adding elements to the binary search tree. So this method here is going to add elements. So for the adding element, we have to do the exactly same thing. So imagine this is the current situation in our binary search tree. We have the 60 on the root, and then we have the 60 on the root, and then we have the children of the root, and so on and so forth. And now we want to insert 101 into this tree. And as we want to insert it, we want to make sure that we have the properties of the binary search tree maintained. So we always going to start from the root. So 60, 101, 101 is bigger than 60. So definitely has to go to the right. So we go to the right. So now 100. So now we have to compare 100 with 101. So 101 is bigger than the 100. So definitely we have to go to the right. So the next right is going to be 107. 107 is bigger than 101. 101 is a smaller. So that means it has to go into the left side of the 107. So we need to add it to as a left child of this node. So how we do that? As you can see, we still, again, we're going to start from the roots, and we're going to keep having this while loop. So either we're going to the left, and either we go to the right. And otherwise, we know that this is going to be a duplicate element. If we cannot go to the left and right, it's basically, it's equal to one of those nodes that we already have. That means we have a duplication, and we cannot accept duplication, so we're going to return false. And otherwise, and then when we're done, we find the location of it. So when we get out of this part of the equation, this if-else statement, and we're getting here, when we know that our parent, we find the parent, and we know that this has to go to the left side or right side of this parent, right? So if so, because we have the currents, right? So if it's going to go with the, when we're trying to add it, then we need to check the gain. So if element is less than the parents, we're going to the left side of it. Otherwise, we're going to add it to the right side of it. So we're creating the element, this new element, and we're adding it into this, and the entire thing come back as a true. That means we were able to successfully add it to the list. So that's pretty easy, right? So implementation of adding elements into the binary search tree is not very complicated. The one that is getting complicated is, okay, and here we're showing it visually what's happening. At this time, we're trying to add 101 again. So we keep going, compare it with 60, with 100, with 101. The value of current keep changing, the value of parent keep changing, where we have to keep track of that. But basically, as you can see, we have two runners. One is the parent, and one is the current, right? So current is keep going until we find the parent. So when we're done with our search, we find the location of the parent. Now we have to decide that if it's going to go to the left side of the parents, which in this case, 101 is going to go to the left side, right? Or have to go to the right side. The next example is going to be 59, right? So we want to add 59. So we start again from the root 60. And it's 59 is less, so we're going to go to the left this time, and then comparing 55 with 59. And now we have to go to, since 59 is bigger than 55, we have to go to the right side. So now we're comparing 57 with 59. And 59 is bigger, so it's still we have to go to the right. So this is going to be the location of it. We find the parents, and now since 57 is less than 59, or basically 59 is bigger than 57, it has to go to the right side of it. So we're adding it to the right child. So searching and inserting is pretty straightforward, and it's you know, also let's just practice the height of this tree now. We have like level 0, level 1, level 2, and level 3. So the height of this tree is 3 maximum, right? So the, you know, even the height of this tree is 3, because the height of this tree is 3 because of the fact that we have one the highest basically degree, or the highest depth of one of our nodes is going to be 3. So the height of this entire tree now has become 3 as well.